24, just a warm-up exercise this morning, similar to what you have done. Right here is a vector field given, and nothing special. Just notice that there's nothing in front of k, the third component. Always constant, but there's something varying here. And we want to compute the line integral along this line, and they didn't give you the parametrization, right? But it's not a problem. Whatever parametrization you choose, the answer will be the same, right? So we choose the simplest parametrization. Okay? So the main task of this problem is come up with your own parametrization that beginning from the -1, 0, 1 and ending at 1, 0, 1. If you just write line between these two, it's unclear which direction we are going, so I specified it here. This is our exercise number 1, if you're not sure. Yes. Where'd it go? All right. Thank you. Yes. Right. But it coincides with a derivative vector, and especially it's exact displacement vector. All right. Make sense? How about parametrization ideal? Good. Start from here that the position vector is relative to 0, 0, 0, right? So you have to figure out this vector. So you go v and displacement vector all the way to the w. That will be v plus w minus v, right? But if you shrink this one by any scalar factor less than 1, then you will arrive at here somewhere. You shrink it, right? So v is still there. It is not scaled. But this w minus v, the displacement vector, is scaled to shrink it there to arrive at somewhere in between that line. So that covers all the position in between this in this line segment. All right? Make sense? I think this is easier to remember than the other version I showed you in the homework. So once you have that parameterization, you can double check. When t equals 0, you plug in 0 there, and that's negative 1, 0, 0, right? 0, 1, when t equals 0, right? When t equals 1, you should arrive right here. T equals 1, you plug it in there, 1, 0, 1, you arrive it right there. And it's linear, there's no t squared or anything like that, so you know it's a straight line, beginning here and ending it there. Make sense? All right. Any question on this one? All right, how many parameterizations are there going from this to that in this straight line? There are infinitely many. You can just change this function to something else. For example, I can write tau t, thing like this, sine t, 0 and 1. Nothing is really happening to 0 and 1 if you notice that. It starts from when t varying from negative pi over 2, pi over 2. Then when t equals pi over 2, what do you get? Negative 1, right? When t is pi over 2, you get positive 1. So this guy is changing from negative 1 to positive 1. So this must be on that line too. If you sketch it, that's exactly the same line. But it doesn't go through, this motion doesn't go through like constant speed. Sometimes fast and sometimes slow because of the sign is involved in there. Doesn't quite look like, this one here is composed, t with composed of something, but there will be some abstract function that make, this one is actually this one, t replaced with some function in there. One half, this one half here, this one half. Yeah, when you make a substitution of this one u, the derivative of du, that's 2, right? When you do the substitution integral, you multiply reciprocal. Right? Remember that when u was a square root of x, then, let's say x squared in the integral, you divide 2x and you change a variable, right? That's a good point. When you integrate, you have to make sure that this one must be with respect to t, or this one with respect to x, but you will not get x here at this point. Another question? Yes.
So in the homework, I was always plugging in the x.
Anything else? All right. That's line integral. And we're just focusing on the mathematical part and how to compute and how to deal with the mathematics. Not much about the work, but they have this one more problem about the work that we need to think about. I think it's worth thinking about it. So here's a force field, slightly different. We did that on Wednesday. And here's a helix path. I'm going to have a picture there. So I'm going to pull that up. So I put the circular cylinder around it so you can visualize from this static picture better. That's the path outside the circle and come back up here, right? So that's the path, and this is where t equals 0, and that's where the t equals 2 pi. And suppose the force field is the same as this exercise example 1. You pick up a unit mass in here. Suppose that this is something, huge bit or ball wired to that. So all you have to do is push this one up or upward here, right? So starting from 1, 0, 0 all the way up to 1, 0, 1, if you plug in those t values, is 0 and 2 pi, and that's what you get. So if you push this along this path all the way up to that, how much work have you done? And that's the question. So here's a scenario. When you push it really hard, a lot more than what you have dealing with this force in there, then of course that when you're pushing at this point really hard like that, and whatever the force is actually you're dealing with is this one, the orthogonal projection of the component you're dealing with in that direction is just this much. If this force is a lot harder than this one, you have residual force, right? Therefore, you keep having this excessive amount of force that causes this one pushed up faster and faster in terms of speed, correct? If you keep pushing it, you're getting faster and faster. Then you have done some work, but what if I'm always dealing with just the right amount coming from that vector field phi? Then you will not have any excessive velocity. You will just keeping in constant speed all the time and pushing it up there, right? So which one did more work? The guy who pushed with the harder force did more work, right? So this is quite unclear. And what do you mean by this one? I could push really hard, right? They're not asking about the gravity, if it is some sort of gravity. Gravity is always there. It didn't push it hard or anything. So work done by this gravitational force or vector field phi doesn't change how hard you push it. But if you really push it hard all the way up to there, then you did more work than the minimum that's necessary. So usually other books, they formulated what is the minimum amount work required by you, push this one from here all the way up there, dealing only with the vector field phi, ignoring friction and other things, right? So this question makes sense. Minimum work required by the person to push this one all the way up to that. What if there's nothing in there? There's no vector field. How much work is required to push this one up there? It's 0. Actually, because of the curvature, if you just push it, assuming there's no friction, it's just unrealistic. Because of the curvature, it might stop. But if it is a straight line, push it all the way up there, for example, like this. Change the path. And if there's no gravity like this, if I just, very short period of time, toss it just a little bit, and then it'll keep rising, right? It doesn't require anything from me except the very momentary impact at the beginning. It'll rise and get there. So minimum work required by me is essentially 0. This time it will be positive because there's something work against our direction, right? Okay? So this question makes sense? So what is the answer in here? The minimum work is the work done by this force field minus. That's it. Because we always work against the vector field in there. So the answer is minus of this thing 0 to 2 pi, right? Of this vector field phi and sigma t dotted with the sigma prime t dt, which you already calculated. I think it was 1 minus 2 pi. Was that right? Something like that. So it's a 2 pi minus 1. So that much of the work you have to do, minimum amount of work, to push you all the way up to here. Okay? Any question about this interpretation of example 2? Make sense? So if they're in the exercise, if they're asking how much work have you done, don't get confused. They really mean what they really mean: the minimum work required by you or what other forces to deal with this different source of force. Any question about this one? Good. Let me make just one remark. You can go ahead and do that. This is a lot simpler path, right? Go straight upward, right? And I think if you calculate this force with this vector field, you get a different work amount. If it is usual gravity field like this, K, negative K, and there's no other things like that, and you go around like this, go straight up like that, it end up at exactly the same work. But this one is not the same vector field. If you go straight here and go around it, they are really different. This is different from different path parameterization, right? This is a completely different path. Same path, different parameterization is a completely different path. But you might recognize this problem from physics, that it doesn't matter how you go up, path around, the work will be the same. Not so with this guy, because it's an artificial vector field, not the one that arises from gravitational field in nature, like that. All right, but you can go ahead and compute that on your own. All right, so this makes sense now. You accept it better. And here is two different paths. You will have the same number. So now they push this idea of invariant property. It doesn't matter how you parameterize it, you will always get the same number. And they use this interesting introduce this notation. First, we start with a path versus curve. This is a physics term. In mathematics, curve is really the path, but physicists use different terms. Path C, for example, y equals x, x between 0 and 1. This inequality does not come with any particular direction. T is coming with a particular direction. This is just a collection or set of number in between 0 and 1. So this is a line segment in xy plane with a slope 1, right? This line segment in there. This is called a path. This doesn't specify how you move around, or doesn't even mean that it is actually motion. It's just the set of positions. For example, if it's in a number line, you understand 1, 2, 3, right? This is called the set of position in the number line. But what about 2, 1, 3? This is a set of position in 2, 1, 3, right? But in mathematics, they're saying these two things are equal to each other. Did you know that? Did you know the set of 1, 2, 3 is equal to set of 2, 1, 3? Right, because you often look at it as a sequence, right? You want to look at the first number is 1, second number is 2, third number is 3. And this one is the first number is 2, second number is 1, and third number is 3. The one with the order, what is this called? Not a set, but what is the other S word that I use? Sequence. If you look at this as a sequence, they're different, but as a set, they're the same. What is a set? It's just a membership. Set is the membership information. Is 3 in there? Yes. Is 3 in there? Yes. They have the same membership about 3. Is 2 in there? Yes. 2 in there? Yes. 1 in there? Yes. 1 in there? Yes. The membership question ended up at exactly the same, right? Then we say these two sets are equal, completely ignoring how they're lined up in the number line, right? Metric and other things. That's a set. That's a path. But what is sigma t? Actual location with respect to time. A lot more information than this one. So do you recognize the difference between path C and sigma t? Physicists call this one a curve. The motion. The path had no motion, just a collection or a set of positions. Now, when you calculate things like this, right, it is all about this path, not your parameterization, right? So this is how we calculate, but they recognize it doesn't matter which sigma t you use. So they wanted to look at it like this: sigma prime t, the position is always there, and position is always there, and you provide your own parameterization, then you enter this derivative. So they didn't use sigma t, they used dr dt. Here's a position. If you have parameterization, now we have a notion of dr dt, right? To, differentiate each component. Then you integrate it like this. That's the right-hand side, correct? They recognize it doesn't really matter how you parameterize it, so why don't we just, as if this was cancel, and use this notation, just phi of a position, and dot it with this formal notation dr. Throw away the parameterization, it doesn't matter. And this t1, t2 doesn't even matter. All that matters is the path, right? So they put that path over there. But this path is not the usual path, it's oriented path. The path comes with a direction. This opposite direction is going to be the negated value, correct? So this is notation makes sense? Simplified notation. Here's a path with orientation, and we just simply write it like this. When you're asked to compute this one, you have to come up with your own parameterization for C and enter this guy and get a number out of it. But they love this notation. So do I. Yeah. That's the notation. We need to practice to get used to this, right? So here it is. Exercise number 2. See for yourself if you understood what I just said with this exercise. C is a straight line segmenting joining from that to that, right? Let's give you the orientation. Let's assume that if they don't say from to specific, always the first one is the beginning and the second one is ending. Let's assume that. Find this value. This is a new notation of the same thing. What is missing here? That is missing, that's 2. What's another thing that usually missing to actually compute this one? Right, parameterization. Sigma t is missing, right? But it doesn't matter which sigma t you use. So you have to come up with your own sigma t and enter this one with the usual t version. That's the problem. So I hope you recognize it's exactly the same problem as this exact exercise 1 we did today, right? Yeah. let's save our time just to formulate down to this one variable integral and not completing it. Everybody knows how to do this one. So how about R? Was this okay? The idea of parametrizing a line segment joining one point to another using V and W? Any question on that part? Getting this R? For line segment, we're always using T from 0 to 1. Yeah. Alright. Then meaning of this one is, get this vector in terms of x and y and z in general. And this one is dr dt. So here it's position. With respect to t, you get -6. And that's 5 and 5. That's a speed vector, right? Because this line is constant. And that's how we parameterize it, at a constant motion. Constant speed motion in the constant direction. So if you do the dot product, -6 times x, here's a 2 minus 6t, -5, it's negative there, y is 1 plus 5t, and 5 times xy, and xy is a product of these two things. And you do the calculation. Does that make sense? What was the purpose of this problem? Let's get used to this notation, right? Yeah, new notation of this line integral. That is missing t. There's no t in there. Path and line, the vector field, which only dependent of positions. Question? All right. How about this problem? This is not an exercise. I want you to think about this problem and answer it quickly, because it's possible. Suppose that vector field at position r, this is position r vector, make sense? And this is the vector phi of r. That's a vector assigned at that point of application, force vector, for example, and is orthogonal to the path of the sigma prime of t. So I think a path is going through like that. That's a sigma t. So orthogonal to sigma prime t. So do you think my picture actually accurately, sketched it there? What is sigma prime t? Meaning of sigma prime t? Velocity vector, right? How does the velocity vector look like? Yeah, maybe that's sigma prime t. Does it look like orthogonal? Right? Yeah. Then what's that going to be? Yeah, the dot product will be 0, right? If that's, if you end up at sigma of r, prime t, if I replace that with a sigma t, that's always 0, right? Wherever you are. So what's the integral value? Yeah, if you integrate 0, you get 0, right? So for example, if it is a horizontal rod there, a bead is attached to that loosely, gravitational field is there, and if I push this one to that over there, like that, how much was the dark work was done by me? There was a certain amount of work done by me. What about the gravity? Gravity and this direction of field heads perpendicular to each other, so the work done by the gravity to move this one to that is nothing. There's no contribution coming from the gravity if I move it like this, right? Yeah, that's the meaning. Alright, few more notation. They're having fun with this parametrization free notation. That's what they're saying. Alright, suppose you have a path, oriented path, right? I don't know the parametrization, but that's the trace. That's the marks in the xy plane. Suppose there's another one that like that. Like this one. But if it with this parametrization, you can look at it as a one curve like that, right? So we're going to denote with this notation. C1 is not a number, right? C2 is not a number. Then what does it mean to C1 plus C2? This oriented curve connected like that, we want to look at this entire thing as a one curve. one path with the orientation. Is that right? Here's an awkward thing. If it is a straight line and that's my C1, right? And we can look at it as an overlap. The other one is C2. If it's exactly the same path with the opposite direction, then we write C1 with this new notation, negative C1. It's not minus C1, it's a negative C1, it's negated. So you can think of it as a C1 plus negative C1, this one over there. But we don't write C1 minus C1. It's not number, right? This is a path. We don't necessarily write this one the zero path. This is just a one path. There's no simplification. Okay? But if you integrate over that, then the effect is that you're going forward with a line, a vector field, or going backward with the same vector field, you end up at exactly opposite sign, so it becomes 0. The integral over that one is 0, but we don't write this curve itself. Path itself is a 0 path. We recognize a different curve, different path. Is that okay? Formality. And this one I just explained it. Negative C means going opposite direction. What happened to the line integral? Just opposite sign. So let me write down what I just said. This is not equal to 0. I don't even know what 0 path means, right? So don't write it like that. But we do have this thing, C1 minus C1, C1 plus negative C1 of whatever vector field you integrate. What is the answer? 0, because this is the same as, sum of these two things. If the C2 is a negative C1, then this whole thing is the same as negative of C1. So they two cancel, becoming 0. What was the question? Okay, yeah. So if you integrate, you have an idea about how they simplify, but this expression itself does not simplify. All right? Good? Line integral. Something is going down, some operations going down there in the subscript level. All right, let's read this problem. It says, C is a parameter of the unit square, 0, 1, 0, 1, not region, this curve and that curve and that curve and that curve. They're all oriented, right? In this way, they provide the orientation counterclockwise direction. So, first sentence makes sense with the picture? Okay. Then evaluate this line integral. If we call this whole thing C, individual path is called C1, C2, C4, but what is C? C1, C2, C3, C4. Right? Joining these oriented paths together, we call it one path. And they want you to calculate the line integral over this one path, if it is like this. So what's the idea? You write it like this, but that's really the same as integral over that, plus integral over that, plus, you can separate it. So integral over here, integral over there, integral over there, all the same function, but over different paths. So you got to calculate this, each individual thing, right? I wouldn't imagine there is one nice formula that parameterizes all three sides at once. So you have to parameterize this one, and parameterize that one, and parameterize that one separately, and parameterize all separate parameterization. Yes, sir. That make sense? All right. This group, please calculate over C1. This group, please calculate over C2. Rebecca's group, please calculate over C3. And Andrew's group, please calculate over C4. And then we're going to collect them together, right? This is not how it's going to be done in the test. You have to do it all by yourself. As an exercise. Exercise 3. I hope you guys agree on each other. Parameterizing then using the vector method, but vector method still works. Oh, this is two-dimensional vector, right? You don't need z here, just x and y, and vector field itself only has a two-dimensional vector. So we're in 2D, not 3D. Well, I guess Andrew was right on that part. But I think that's a coincidence. In general, doesn't work. Yeah. So, excited about the test? Yes. All right. How about C1? That makes sense? This is always y equals 0, so I put it in there. How x coordinate varies from 0 to 1. That's natural orientation. Yes. Okay. Uh-huh. That's right. That's right. Yeah. Andrew was wrong. Yeah. I knew it. 1 minus t squared, that's x there, you're correct. And multiply that in there, the negative still on there, dt. All right? Yes, I think these two numbers are the same number, not opposite sign. If you do the change of variable u,